here, excellent. All right, so we are still in the, so this is again section, 6.2 combined with section 6.3, change of variables. Okay, so I guess last week I explained a little bit this is a change of variables for double integrals. So let me just remind you. So we have this the following theorem. So we first we are interested in double integrals, of course. Double integrals. Okay, so we have the following theorem. So this theorem would allow us to change the variables in double integrals. So suppose we have a change of variables. A change of variables given by, so it's given by some transformation t. So t of, let's say, t of uv equals to, say, x of uv, y of uv. So x and y, they are functions of u and v. So this transformation t is 1-to-1. With the image, so the image of some region R is equal, so the image of R is equal to D. So where R, so R is a region in the plane, where R is a region in some region in the plane. So then, so here's the formula. So if you have the double integral in terms of x and y, so let's say you have this double integral over d. So d is also a region in the plane, right? So we have this double integral over d. D is some region in the plane of some function f of two variables, x and y. Okay. So if you decide to change the variables from x and y to u and v, then the new integral would be, so double integral over r. Okay, and then that would be f of, so you need to substitute x in terms of u and v and y in terms of u and v, right? So you're gonna end up with some function of u and v. Anyway, guys, we'll have some examples in a couple of minutes, right? So your f now is going to be a function of u and v, right? And then the most important thing here in this formula is that this area element, right? This dx dy, this is my area element in xy coordinates, right? In xy coordinates, this dx dy is gonna becomes actually the absolute value of the Jacobian. So here we're gonna have the absolute value of the Jacobian of x and y with respect to u and v. All right. Du dv, right? So here we're gonna have du dv. Okay. So the Jacobian, this where this partial xy, partial uv. So this is my Jacobian, and it's actually equal to the determinant of the matrix, the derivative matrix. So it's like partial x, partial u, partial x, partial v, partial y, partial u, right? Because x and y both are functions of u and v, right? So partial y, partial u, and then partial y, partial v. This is a partial derivative, right? and that's equal to, so the determinant of this matrix is just, you know, you cross multiply. So it's just a partial x, partial u, partial derivative of x with respect to u, times partial y, partial v, minus partial x, partial v, and then partial y, partial u. Okay. Now, so the important thing, guys, so what we have to remember here is that, so the dx dy, you know, your area element dx dy becomes this Jacobian, you know, this Jacobian du dv, and then of course you have to be careful with your region here. So so when you integrate with respect to x and y, so you're integrating over this region D, right? You have this region D, but then when you integrate with respect to U and V, so you have to integrate with respect to this region R, right? So here, relation between D and R, remember that the image of R under the transformation T is equal to D, right? So that's the relation between these two regions, D and R, right? The image of R under T is D. Anyway, so let me just explain here why this theorem is true. So what's the idea here? Why this dx dy becomes this Jacobian, you know, du dv. So the idea is the following. So we remember, guys, we at some point, I think last week, we discussed linear transformation, right? So we said if you have, you know, if T is a linear transformation, remember a linear transformation was like, so when you have like a matrix, okay, so this means, it means that T of uv is equal to some matrix capital A, you know, times the column uv, where A is, where the capital A is the matrix given by the constant, you know, it's a 2 by 2 matrix, so A, B, C, D, right? Okay, so that's what I call, what I mean by a linear transformation, right? It's just, or I mean, in other words, T is just, you know, T of uv is just, you know, A u plus B times V, right? That's the first component, and then you have like Cu plus dV. That's the second component, right? So that's what I mean by linear transformation. There's some matrix times this column. So here it's a multiplication, matrix is multiplication here, right? It's capital A is a matrix. Anyway, so we said, I mean, this is just some linear algebra, but we said that, you know, the area, so if you have some region R, okay, so let's say you have some region R, and capital D is the image of the region R under the transformation T, right? So we discussed a little bit, you know, when you have this linear transformation, we discussed a little bit the relation between the areas of R and D, right? We said the area of D in case of linear transformation, right? So then we said the area of D, okay, this region D, right? You have, so, you know, so you have this region R, right? This is R. And then you have this transformation T. And the image of this region R would be another region, of course. And this would be the region D. Let's say this is your D, all right? Then we said the relation between the areas of D and R is the following. So area of D would be equal to the absolute value of the determinant of the matrix A times the area of R, right? Like we had an example with the squares, right? I don't know if you remember the example with the squares. We had like, let's say this is a square. We had an example with the square here. The area is equal to 2, right? And here we had like a square the area of the square, this square was 1, right? Area here is 1, okay? But then when we computed the determinant of the matrix A, its absolute value is equal to 2, right? And so that explains you know, the relation between the two areas. But anyway, but this isn't the case when we have a linear transformation, right? And we said not all the transformations are linear, right? Because here in our theorem, this change of variables, this transformation T is not necessarily linear, right? It could, it's not linear, and not all the transformations are linear, right? We had a couple of we discussed this case of r cosine of theta, r sine of theta, like the polar coordinates, and we said such a transformation is not linear, right? Anyway, so not all the transformations are linear, so we cannot really just apply this formula in our theorem, because the capital T in the theorem is not linear. But then we can still explain this relation between these two area elements, right? The area element here, dx dy, we said it would be equal to this determinant of this Jacobian dv dv, right? So the question here is why. My question is the following. So why dx dy is equal to this Jacobian du dv. All right. So, I mean, that's the main thing in this theorem, this relation between these two area elements, right? So why this is true? Because, I mean, again, my T is not necessarily it's a linear transformation, right? The idea here, guys, so, you know, so this, again, this dx dy or this du dv, this is just the area of a very small region in your space, right? So we have, let's say here you are using this u and v coordinates, and here you are using this x and y coordinates, right? Now, so what we are saying is that, so we have this region D here in the xy coordinates, and we have some region R here in the uv coordinates, right? And of course, the image of R is this capital D. Anyway, so when you say dx dy, so what does it mean really dx dy? Well, dx dy is just the area, the infinitesimal area of a very small element here in D. So when you say dx, dx is just you know, a change in it's your length element along the x-axis, right? It's just a small change in the in your x-axis, right? That's like the length of a very small subinterval along the x-axis. dy is the same thing. dy is just a small change in the values of y. So this is dy, right? So when you say dx dy, it's just the area of this very small rectangle, right? This is here, this is dx, and here is dy, right? Now, du dv, the same thing. So du would be just a small change in the length of your interval along the u axis. So this is here, it's du, and here dv is just a small change in the values of the v, right? So when you say du dv or du times dv, it's just the area of this very small rectangle. All right. Now the thing, guys, is that so going from this very small rectangle, this red rectangle here, this one here, to this rectangle, blue one here, the xy coordinates. So the relation is the following. The thing is, when you compute the derivative, dx, okay, dx in terms of u and v, dx actually would be partial x. You remember, x is supposed to be a function of u and v, right? Okay, so x is a function of u and v. So you can compute the derivative of x with respect to u and the derivative of x with respect to v, right? So then dx would be actually partial x, partial u, du, and plus partial x, partial v, dv. All right, and then same for dy. So when y is also a function of u and v, right? So then dy is actually partial y, partial u, du, and then plus partial y, partial v, dv, right? So you see, guys, here dx is just this partial x, partial u times du plus this partial x, partial v, right, dv, and etc. Right? So then actually you can write this like, so you can write this like, if you want to write this in terms of like using matrices, so you can say, you know, dx dy is actually this partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v, times du dv. Okay. Here, this is a matrices multiplication, right? This is supposed to be a matrices multiplication, right? So this is exactly like in our case of linear transformation. Remember linear transformation? Here, this capital A, this matrix capital A, it's A, B, C, D, right? So again, we have this. So this partial x, partial u, partial x, partial v, etc. This would be like my matrix capital A. So this is like my capital A. Okay, this 2 by 2 matrix, right? So what we are saying here in some sense is that this, you know, dx dy is equal to this matrix A times du dv. Okay, so actually we have this, you know, this A here, this is a matrix. So we have a linear transformation here. So this is a linear transformation. Okay, and since it's a linear transformation, then then we can just apply, you know, this remark we had for linear transformations. We said then the area of D here is equal to this absolute value of determinant of A times the area of R, right? So then in our case, the area of D would be, well, here we are talking about this small rectangles, right? So here we're gonna have this dx times dy. That's the area of my small rectangle. So then dx, so then, you know, so then dx dy. So this is the area of my small rectangle, very small rectangle, would be equal to, you know, determinant of A, absolute value of determinant of A times du dv. All right, and du dv, that's the area of my small rectangle, infinitesimal change in the area element, right, with respect to the u and v coordinates. So this is the area of my small rectangle here. Okay, so this is why we have this theorem, because we are, in terms of dx and dx dy du dv, we do have a linear transformation, right, in terms of again of these differentials dx dy du dv. We have a linear transformation. So capital T itself is not necessarily linear transformation, but this change of the infinitesimal change of the areas going from du dv to dx dy, it's actually a linear transformation. Okay, does it make sense to you guys? So this is actually the idea of this theorem. I mean, this is actually the proof of I would say this is the proof of the theorem, right? Any question, guys? I mean, does it make sense to you? So going from this dx dy du dv, this is really a linear transformation. So that's why we have this the absolute value of the Jacobian. And remember, Jacobian was the determinant of this matrix A, right? We said, so the Jacobian by definition is this determinant of this matrix A. All right, so which is of course partial x, partial u, partial y, partial v, minus partial x, partial v, partial y, partial u. Okay. All right, any question, guys? All right, so let's have a first numerical example. I mean, last week, I think we had an example, but it's for a single variable. I was explaining, so last week I explained that this formula actually, well, here it's for double integrals, but if you forget about the y and the v, okay, so if you just work with x and u, right? So then this formula would correspond to the substitution, right, for integral of single variable, right? But anyway, so now let's have a first numerical example in case of double integrals. So first example, again, guys, please feel free to ask questions if you have any, right? So first example, we're gonna have two examples, and then I'm gonna give you an exercise, guys. Okay, so examples. First example, I'm gonna go with first, I'm gonna go with like a linear transformation, and then we're gonna have a non-linear transformation, right? So let's say you have let u equals to x plus 2y, okay, and v equals to x minus y. Okay, and the question is so we have to evaluate the double integral of the function y dx dy over some region D. So the region D, where D is bounded by the lines y equals to 0, y equals to x, and then the third line is x plus 2y equals to 8. Okay, so we need to evaluate this integral using the change of variables u and v, using the change of variables u and v. Okay, so what I'm saying, guys, here in this example, so we have this double integral. So this double integral, it's over some region D, but it's a double integral in terms of x and y's, right? So we are using the x and y coordinates here, right? This is in terms of x and y, and the question is to evaluate this integral using this change of variables u and v. So we need to change the variables from x and y to u and v, right? So of course, the goal of this example here is to apply our theorem, right? So again, let me just remind you the theorem. So the theorem says that, so this y here, this is our function of x and y. This is my f of xy, right? This is my f of xy. And this is my area element dx dy, and here's my region D, right? So the theorem says, so let me just write down again for you the theorem, guys. So the formula says the following. So the theorem So if you want to apply this change of variables, then so we have this function of x and y, dx dy over some region D. This is going to be equal to, so if you want to change to u and v, then first your function f is can be expressed in terms of u and v. Okay, then you have to multiply by this absolute value of the Jacobian. Am I recording this session? I forgot. Yes. Okay. Thank you. All right. So yeah, the determinant of this Jacobian, right? X, y with respect to u and v, and then du dv, right? Du and then du dv. All right. So here in this exercise, so what we are saying is that this function f of xy is equal to y, right? And this region D is this one here, the one bounded by y equals to 0, y equals to x, and x plus 2y equals to 8. Anyway, so we want to apply this this theorem. So there are a couple of steps actually before evaluating the integral. So first step, so steps. So if you want to apply this formula or this theorem, the first step would be to so step 1. So you have to first solve here. Okay, so first step, you need to find f of x u x u v, y of u and v, all right? And you have to solve. So you have to solve actually for x and y. Okay. So if you want to express this function f of xy in terms of u and v, you need to solve for x and y. So you know that what's given here in the problem is that u is x plus 2y, right? And v is x minus y. Okay, so that's what the change of variables, u and v, right? Now, so in this first step, what we have to do, guys, we have to solve for x and y. So we have to express x as a function of u and v, right? And y as a function of u and v. So we have to solve for x and y, right? Here, I mean, in this form, what we are saying is that u is a function of x and y, right? U is equal to some function of x and y. And here, same, v is some function of x and y. So what we have to do is to solve for x and y. For example, if you want to solve for x, you can say, well, let's solve for x for example. Solve for x. Okay, so let's call the first equation here. This is my first equation. U is equal to x plus 2y, and the v is equal to x minus y. That would be my second equation, right? So for example, if you multiply, you want to solve for x, right? You want to solve here for x. So for example, if you multiply v by 2, so let's say you do 1 plus 2 times 2. So the first equation plus 2 times the second equation, right? So if you multiply by 2 the second equation, right, you're going to have minus 2y. In the first equation, you have plus 2y. And so the sum, in the sum, the y will cancel out, right? So so what we are saying here, guys, so we have this first equation, which is u equals to x plus 2y. Now, 2 times the second equation, we're going to have 2v equals to 2x minus 2y, right? Now, if you do the sum, then you're going to have u plus 2v equals to 3x. Sorry, 3x here. And then plus 2y minus 2y would cancel out, right? And that's why I multiplied the second equation by 2. So then y would cancel out. So now I can solve my x. So then x is just, so my x is just, so you divide by 3. So my x is u over 3 plus 2/3 times v, right? So that's my x. Now I want to solve for y. You can just use, for example, the second equation. You know the value of x in terms of u and v. So let's say just use the second equation, right? From the second equation, you can say, well, the second equation is v is equal to x minus y. So then you want to solve for y. So then y would be, you move y to the left side, right? So then y would be x minus v. X is, you know, the value of x in terms of u and v. It's u over 3 plus 2/3 of v minus v, right? Minus v. So then, so this is the value of x. Right. Now, y would be equal to, if I'm not mistaken, u over 3, 2/3 minus 1. So that's 2/3 minus v over 3. So that's minus 1/3. So that's just minus v over 3. Right. So that will be my y. So, all right. So this is y. Okay. So I got my x. I got my y. So now I can express my function f in terms of u and v, right? That's, so in the first step we said we have to solve for, so we have to solve for x and y, and then we have to find f in terms of u and v. So what's f in terms of u and v? So conclusion here from this first step, the conclusion is the following. So f of u and v so my function f is equal to y, right? Now y is equal to u over 3 minus v over 3, right? So this is my function f in terms of u and v, right? So we got the expression of f in terms of u and v. Again, this function here, y, guys, y is the function inside the integral. So the function that I have to integrate, right? In the problem, where's the problem? Right here. So you see here, guys, inside the integral, I have this function y. So that's my function f, right? So that's equal to y, and we just solve for y in terms of u and v. So then my function would be just this u over 3 minus v over 3, right? That's the first step. Any question about the first step, guys? So we have this change of variables, u and v. So first, you have to solve for x and y, and then express your function f in terms of u and v. Now, second step would be to compute the Jacobian, right? This is step number 2. So step number 2. So we have to find the Jacobian. Okay, so what's the formula of the Jacobian? So that's the determinant of this matrix, the derivative matrix. So it's just partial x, partial u, partial x, partial y, partial v, minus partial x, partial v, partial uy, partial u, right? So we need the partial derivatives of x and y with respect to u and v, right? So we know the formula for x and y in terms of v, u and v, right? So x is equal to, so we said x from the first step. So from the first step, we said x is, well, here's x in terms of u and v. It's u over 3 plus 2/3 of v, right? So then, so this is from first step. This is from step 1. Right? So we are saying x is u over 3 plus 2/3 times v. And then, so this is my function f in terms of u and v. So now what's partial x, partial u? So partial derivative of x with respect to u. So let me just remind you guys, when you compute the partial derivative, like here, x with respect to u, x is a function of u and v, right? So when you compute the derivative of x with respect to u, you have to assume that v is a constant, right? So here you have to assuming v as a constant, right? Okay, so I mean, so we have u over v derivative with respect to u. It's just the 1/3. So that will be 1/3, right? The constant in the denominator of v. And then there is this 2/3 of v. I mean, v is a constant, so the whole thing is just constant. So the derivative of that would be 0, right? So it's just 1/3 plus 0. It's 1/3, right? We need partial x, partial u, then we need partial x, partial v, partial x, partial v. Now, when you derive with respect to v, then we consider u as a constant. So u here is a constant, right? I mean, so then if you consider now u as a constant, though the derivative of this u over v, that will be 0. And then derivative of 2/3 of v, of course, that will be just 2/3. So this is just 0 plus 2/3, that will be 2/3. Okay. Same thing for y now. I mean, y is as a function of u and v. We said y is, let me see. I'm sorry. Yes, so it's u over v minus v over v. So it's so y is u over v minus v over v. So then partial y, partial u. V is a constant, so that will be again 1/3. Partial y, partial v. U is a constant, so that's minus 1/3. Guys, please let me know if you have any question about this partial derivative. I mean, that you're supposed to know this from Calc 3, but I mean, again, if you have any questions, just let me know. So that's for the partial derivatives. And once you have the partial derivatives, then you can compute your Jacobian. So then now the Jacobian, so conclusion or the answer here. So this is my step number 2. And then this is step number 2. We said we have to find the Jacobian, right? So this partial x, y, partial u, v, my Jacobian, which is, we said it's partial x, partial u, partial y, partial v, minus partial x, partial v, partial y, partial u. So that would be equal to partial x, partial u is 1/3. Partial y, partial v, 2/3. Times 2/3 minus partial x, partial, sorry. What I was saying, partial x, partial u is 1/3. Partial y, partial v it's negative 1/3. Sorry, it's not partial x, partial v. It's partial y, partial v. Sorry, here this is, so partial y, partial v. It's negative. Sorry, negative 1/3. Right. Minus partial x, partial v. That's the 2/3. Right, that's the 2/3 here. Partial y, partial u is this 1/3 here. So times 1/3. So then the answer would be, let's see. All right, so that would be equal to negative 1/9 minus 2/9. That's minus or negative 3/9, and that will be negative 1/3. Okay, so my Jacobian is negative 1/3. Again, guys, what's the interpretation, the geometric interpretation of this negative 1/3? Well, this negative 1/3 is actually the relation between the area of a very small very small rectangle in terms of the X and Y coordinates, and a small rectangle in terms of the U and V coordinates, right? Anyway, so once you got the Jacobian, now the third step, I know there are so many steps, but that's how it works. The third step, so we got the function f in terms of u and v. We got the Jacobian. Now the third step is to find the region. So this is step. This is sorry. So this is the step number 3. Right. So what's the step number 3? Well, let me just remind you of the formula. Here's my formula. So we got the function f in terms of u and v, right? We got this. We got the Jacobian, right? Now the region R. Okay, so now the question is, what's this region R? We know the region D. D is this region D here in the original integral is this, right? D is this, D is bounded by the lines y equals to 0, y equals to x, and etc. Right? So in this third step, we have to find this region R. So find the region R. Okay, so the region R is in terms of u and v coordinates. So the main thing here is that, so this region R is actually in terms of in the u and v coordinates. Okay. So my region in the x and y coordinates is D, right? So D, this is our this is the region in the x and y coordinates, right? Now I want to find the corresponding region in the UV coordinates, right? So D is so this is included in the question, right? So this is D is bounded by, we said y equals to 0, y is equal to x, and then x plus 2y is equal to 8. Okay, so the goal now is to express these equations. So you have to express those equations, y equals to 0, y equals to x, etc., in terms of u and v. In terms of u and v, right? So anyway, so I mean, you can sketch this region D if you want. I mean, it's not really, you don't have to do it. But if you want to sketch this region D, well, this region D would be, so here we are using the x and y coordinates, right? So first we have y equals to 0. So here is y equals to 0. Right? And then we have y equals to x. So here's the line y equals to x. And then the third equation is, I'm going to use the green, let's say. The third equation is x plus 2y equals to 8, or if you want to solve for y, so then y would be 4, minus x over 2. Okay. So here is somewhere, so if let's say x is 0, you're going to have, so let's say, so the line would be somewhere here. Okay, so this is the line x plus 2y equals to 8. right? Anyway, so my region D is this one here. So it's bounded by the 3 lines. So here's my region D, right? That's my region D. Okay. Now, I want to express this region D in terms of the U and V coordinates, right? So what we do, guys, is you have to take each of the equations and you have to express them in terms of U and V. So first equation is y equals to 0. Y equals to 0. So what does it mean for y to be 0? Well, y in terms of U and V. So remember, guys, we said y is equal to, in terms of U and V, y is U over 3 minus V over 3, right? So then U over 3 minus V over 3 is equal to 0. Okay, so then U minus V is 0. So then U is equal to V. Okay, so the y equals to 0 becomes U equals to V. Okay, that's the first equation, right? Second equation is it's y is equal to x, right? Line y equals to x, so it's y is equal to x. So y is equal to x, then that will be y is this U over 3 minus V over 3 equals to x. X is U over 3 plus 2V over 3, right? So then there is U over 3 in both sides, so that cancel out. And so that's actually V is equal to 0. So then V is equal to 0. So that's like my second equation, right? Now, third equation is, we're almost done, guys. I promise. I mean, there are many steps here. I know it's sometimes just too much, but it's not that bad. I mean, you have just to be careful of the equations, then it will be fine. So then third equation is x plus 2y is equal to 8, if I am not mistaken. Let's say, yes, x plus 2y is equal to 8. So then x is equal to, in terms of U and V, x is, I think it's U over 3 plus 2V over 3 plus 2y. So that will be 2 times U over 3 minus 2V over 3 equals to 0. Right? So the 2V over 3, 2/3 of V, that cancel out. And then we have, where is it? Equals to 8, sorry. This is, okay, it's equal to 8, right? So that's on the left side, that would be just U, right? 1/3 of U plus 2/3 of U, that would be 3 over 3 U, that's U, so that's U equals to 8. Okay. Now I got my, now I got 3 equations, U equals to V, V equals to 0, and U equals to 8. So now I can sketch my region R. Sketch the region R. So we have U equals to V, V equals to 0, and U equals to 8. So in terms of U and V coordinates, my region D becomes, so this is U, this is V. So V is equal to 0. This is V equals to 0. Sorry, I said V equals to 0, not U. Right, so I was saying V equals to, well, U equals to V. Let's start with U equals to V. So that will be this line here. This is U equals to V. And then we have V equals to 0. So here is V equals to 0. This is V equals to 0. Right, and then U equals to 8. So I'm gonna need 8 on the U axis. So this is 8 here. Right, so U equals to 8. That will be this line here, this vertical line. This is u equals to 8. Right, so now my region R, so my region R would be this region here. This would be my region R. Okay, so you see my region in the XY coordinate is this one here. Okay, now in terms of U and V coordinates, my region is this one here, this right triangle, right? So what are the bounds of this region R? So the bounds of R, it's just a triangle, right? Bounds of R. Well, you can say, for example, V. So it's just this, it's just this triangle, right? So the V, for example, goes from the bottom here. This bottom is V equals to 0. The top here, this point, the V coordinate is equal to 8. So this is V equals to 8 here, right? So we have this segment, horizontal segment here in the bottom, that's V equals to 0. And then the top, I have the point with the V coordinate equals to 8. So you can say, for example, here, V is between 0 and 8. Okay, now what about U? U is between the graph of these two functions here, right? So here U and here U. So on the right side here, U is equal to 8. And on the left side here, U is a function of V, and it's actually equal to V, right? This is U equals to V. So,
excuse me.
Yes.
Does the order of integration in this problem matter? I mean, can we say that U lies between 0 and 8?
Yeah, no, you can also start with the U saying U is between 0 and 8. Yeah, no, that doesn't matter. I mean, you can.
So if at the end we will have dV, du, and not du, dV, it doesn't matter.
Yeah, it's up to you. Yeah,
okay.
Absolutely. Yeah. So that's a good point, actually. That's a very good point. Yeah, so I need to mention that actually. So yeah, so for U is that would be between V and 8, right? Now, as you said, so this is when you have du dv. So this is if you have, I mean, V is between two constants. So that's the last integral. That will be with respect to V, right? Because your V is between two constants. So that'll be your last integral. So in this case, you have du dv. Now, if you, as Enrique, I think, said, instead of starting with V, you can say,
no,
well,
it was me.
Sorry. Oh,
no, it's okay.
Sorry. So then U would be between 0 and 8, right? So let me just, again, here's your triangle. You are saying U is between, so here's this point here. The U coordinate is 0, and this line here, a segment here, U is equal to 8. Now your V would be between these two graphs. So this one here in the bottom, that's V equals to 0. So V is between 0 and this line here in the top. This is V is equal to U. So here, so V between 0 and U. Okay. So it's up to you guys. All right. So we are almost done. And now we can evaluate our double integral, right? Sorry, I mean, I'm probably because I'm doing all the details here. That's why it is taking a lot of time. But I mean, at least if I do one example in doing all the details, then probably you would have no trouble, with the exercises. Okay, at least you can follow, the steps and etc. All right, so yeah, now the last step, and finally we can evaluate our double. This is step number 4. Step number 4. So, in the step number 4, so our double integral over d of the function y dx dy. So the formula says then that would be, in terms of u and v, that would be the double integral over r, the function in terms of u and v. So we have to express this y in terms of u and v. So we did this in the first step. So step 1. This is in the step 1. So we said our function y is just u minus v over c. right? And then we need the Jacobian, actually the absolute value. So be careful here. We need the absolute value of the Jacobian. So partial x, partial y, partial u, absolute value of the Jacobian, right? And then let's say du dv. Okay. So of course, again, guys, you can pick instead of du dv, you can use dv du, right? It's up to you. So that'll be equal to a double. So this might u over 3 minus v over 3 times absolute value. So the Jacobian was negative 1/3, right? This is from the step number 2. So from the step number 2, so step number 2. All right. So it's the absolute value of negative 1/3. Well, so du dv. So in case of du dv, so then the region R would be, so then first u is between v and 8. V and 8, and then v is between the two constants, which are 0 and 8. Okay. If you pick dv du, then v would be between 0 and u, and then u between 0 and 8. Right. So that would be equal to, I don't think I'm going to do this integral because just because it would be too much. I mean, it's very easy to integrate. Actually, it's not really bad. So times this, so that would be u over 9 minus v over 9 du dv. Okay, and then it's and then just the double integral. It's not hard to compute. All right, it's just some powers of u and v. All right, so I won't actually evaluate this integral because it's gonna take a lot of time, and I need to do another example. Okay, so but this is really easy to compute. Okay, this is easy to compute. I don't know if I have the answer for this. Let me see if I actually I do not have the answer, but it's just a very easy double integral. Okay, any question, guys? All right, so let me do another example instead of.
I have a question.
Yes, please.
Do we need to multiply by Jacobian in the integral? Can't we just put it out of the integral, the coefficient?
Yeah, it's because it's a constant, right?
Yeah,
it's a constant in this case. But we'll see, like in the next example. Yes. So this Jacobian, it's supposed to be a function. It's not necessarily a constant, but in this case, it's a constant. So that's actually another good point. So my next example, that's why I'm going to do another example before the exercise. So another example where the Jacobian is not a constant. So my next example is the polar coordinates. Okay. So what's the polar coordinates? Well, that's they are given by the following transformation. So t of actually r and theta is equal to r cosine of theta, r sine of theta. So r here means the radius. So r here is supposed to represent the radius. All right, and sorry, this theta here is my angle. My angle with respect to the x-axis. So in some sense, what I'm saying here is that my x coordinate is equal to r cosine of theta, and the y coordinate is equal to r sine of theta. So that's my change of variables here. So this is supposed to be my x, which is a function of r and theta, and this is supposed to be my function y in terms of r and theta, right? So so what I'm saying here, guys, so if you have, this is x, y, you have some point here, I don't know, let's say this is the point 2, 3, right? So here's my x is 2, my y is 3, right? So what I'm saying, instead of using this X and Y coordinate. So by the way, guys, the X and Y coordinate are called the Cartesian coordinate, right? So let me just write down here for you. So the X and Y coordinates are called Cartesian coordinates. So instead of using this Cartesian coordinates, I'm going to use the polar coordinates. So polar coordinates, so first we have the radius. So first you need the radius of this, so distance of this point from the origin. So that will be my radius r. Right, this is my radius r. That's the distance from your point to the origin, 0, 0, right? And then theta, that's the angle between the x-axis and your point, right? This is theta. Okay, so what I'm saying, guys, is that if you give me a radius, some radius and some angle, then I can find a unique point which corresponds to those angle and radius, right? So for example, if you say radius 4 and angle, I don't know, pi over 4, so then I can find a unique point, right, which corresponds to those coordinates, to those radius and angle, right? Anyway, so that's my polar coordinate. So for example, and this is an important remark, is that the r is actually radius, because if you do x squared plus y squared, that will be, because cosine squared plus sine squared is equal to 1, that will be r squared, right? That's why this r here represents the radius, right? Anyway, so for example, let's say you want to evaluate the area of the disk of radius 1. So let's say, so here's my the exercise, or not the exercise, but the example. Then I will give you an exercise, guys, in a couple of minutes. So let's say you want to evaluate the area of the disk of radius 1. So with this example, we see why this polar coordinates, sometimes they make the integral very easy to compute. So sometimes they are very, very useful. Okay, so let's say you want to compute the area of the disk of radius 1, right? The area of the disk of radius 1. So we have the circle here. This is 1 here. Of course, this is x squared plus y squared equals to 1, right? You have the circle. So your disk is the interior of this circle. So here's my disk D, right? So you wanna compute the area of this disk, the interior of the circle of radius 1, right? So if you want to use the Cartesian coordinates, the x and y, then you're gonna have like some trouble, like because, well, first you have to describe this region D in terms of x and y, right? So you may say, well, you can say, for example, you can say, well, your x or your y, for example, let's say you start with x, you can say your x is between -1 and +1, right? Then y would be between, these two functions here. This one here, this is y equals to positive square root of 1 minus x squared. And the one in the bottom, it's minus, so this is y equals to minus square root of 1 minus x squared, right? And you have these 2 points. This is x -1, and this is x +1. So these 2 points, -1, +1, they are connected by these 2 graph of functions, right? The positive square root and the negative square root of 1 minus x squared. Anyway, so if you use the x and y coordinates, so x is between -1 and +1, y is between this negative square root of 1 minus x squared and positive square root of 1 minus x squared, right? So then the area of the disk of radius 1, that will be the double integral, supposed to be the double integral over the disk of the constant function 1 dx dy, right? But then or dy dx. But then, so that will be, for example, in this case, that will be 1. Here's dy dx. So my x is between these two constant, -1, +1. So that will be my last integral here, bounds of my last integral. -1, +1. My y is between two functions of x. So negative square root of 1 minus x squared and positive square root of 1 minus x squared. But you see, guys, you have some trouble here. I mean, with this square root of 1 minus x squared, you know, you have to use some, you know, substitution here with the trig, x equal to sine or cos sine of theta or whatever, etc., etc. So this is kind of not easy to compute, right? So with this square root of 1 minus x squared, right? But if you use the polar coordinates, in terms of polar coordinates, okay, so so this disk here corresponds to the interior of this circle of radius 1, right? So the radius r would be between, you know, so x squared plus y squared equals to 1. So your r, the radius r for this disk would be between, the radius would be between 0 and 1, right? The radius r between 0 and 1. So the radius r is between 0 and 1. And their angle theta, because this is the whole circle or the whole disk, right? So then your angle theta is going to go from, you know, from 0 to 2 pi, right? So the angle theta is between 0 and 2 pi. That's because we have the whole disk or the whole circle, right? So it's the whole circle. Okay, so your angle theta is from 0 to 2 pi. Okay, so so then the area of my disk which is in terms of the x and y coordinate, would be this integral of 1 dx dy, right? Over this disk D, right? Now, if you use the polar coordinates, so x is equal to r cosine of theta, y is equal to r sine of theta, right? So you're going to have this function 1 again, okay? But then you're going to have the Jacobian, right? So I'm changing the variables here, right? I'm going from xy to this new variables r and theta, so I'm going to need the Jacobian. So it's partial xy, partial r and theta, right? Dr d theta, right? R is, the radius r is between 0 and 1, and the theta, because it's the whole circle, so it's from 0 to 2 pi, right? So here, r is from 0 to 1, and theta is from 0 to 2 pi, okay? Now I have to compute this Jacobian, right? Well, so if you could compute the Jacobian, I mean, x as a function of r and theta is equal to r cosine of theta. So then, for example, you say partial x, partial r. You consider here, you assume theta as a constant. So partial x, partial r, for example, that would be cosine of theta. Partial x, partial theta, right? The derivative of cosine, it's minus sine. So that would be minus r sine of theta. Okay, so here, of course, you consider r as a constant. All right, do the same for y. So let me just write quickly here. So y is supposed to be r sine of theta. So then partial y, partial r. that would be sine of theta, and partial y partial theta. Derivative of sine is cosine, so that would be r cosine of theta. So when you compute the Jacobian, so by definition, it's partial x, partial r, partial y, partial theta, minus partial x, partial theta, partial y, partial r. So partial x, partial r, that's cosine of theta, partial y, partial theta. Where is it? Yeah, it's r cosine of theta minus partial x, partial theta. That's minus r sine of theta. So it's minus r sine of theta. And then partial y, partial r, it's sine of theta. So that would be equal to r cosine square of theta minus minus, that would be a plus r sine square of theta. And if you factor out the r is a common factor, that would be r times cosine square plus sine square, that would be r times 1, right? So then the answer is r. So the Jacobian here, you see guys, for the polar coordinates, the Jacobian is r. And it's absolute value of r, of course, but r is the radius. So the radius is supposed to be positive anyway, right? So the radius, it goes from 0 to infinity. So it's positive anyway, the r, right? So that's my Jacobian. So this is my Jacobian. And in this case, the Jacobian is not a constant. It's a function, right? So then now I can compute the area of my disk. So that will be, we said 1 here, the Jacobian, the absolute value of the Jacobian. It's the absolute value of r, but r is positive, so it's just r. So it's r dr d theta, right? R, we said the radius is between 0 and 1 because it's just a circle for radius 1. So it's the radius from 0 to 1. And theta, it's because it's a whole circle. So it's going to go from 0 to 2 pi. And this is very easy to compute, right? I mean, you integrate with respect to r. So here, just be careful, guys. So now you have this function 1 times r. So it's r here, right? So the integral of r, so this is r. So integral of r with respect to r is r squared over 2. So this is r squared over 2, evaluated between 0 and 1, the theta, right? So that will be half minus 0, or 1 squared. Of course, that will be 1. So it's half minus 0, the theta. Okay, integrate the half with respect to theta. So that's theta over 2 between 0 and 2 pi. And so the answer is pi. Okay, so you see here, guys, when you change the variables to polar coordinates from the Cartesian to the polar coordinates, then the area of the disk is very, very easy to compute. So what it's saying is the area of the disk is equal to pi. Okay, so this is equal to pi. Any question, guys? So you see, so this is another, so this is an example where the Jacobian is not a constant. So you just be careful with that, of course. So here's an exercise for you. And after the exercise, we're supposed to do the change of variables for triple integrals, right? And I have a couple of examples, but I don't know if I have time. We'll see. Anyway, so here's an exercise for you. I'm gonna just probably give you one. I have 2 exercises actually, but I think I'm gonna keep one of them for the homework, and I'm gonna give you just one of them. So the exercise. So let's say you have D. It's actually the parallelogram. Bounded by y equals to 2x, y equals to 2x minus 2, y equals to x, and y equals to x plus 1. Okay. We have to consider the change of variables. So u is equal to, let's see, it's y minus x, and v is y minus 2x. Okay, so we have this change of variables u and v. So the question is, of course, to evaluate. So the question is evaluate. So this is this exercise here is very similar to my first example. So my advice is just to try to follow the steps in my first example. So evaluate the double integral of the function xy dx dy over this region D over this parallelogram, okay, by making the change of variables. So again, this is very similar to my first example. So you can probably try to follow the steps in the first example. All right, guys, let's say you have, I'm gonna give you probably, let's say 10 minutes to think about this exercise. And then after this, we will move to the change of variables in case of triple integrals, all right? So let me just probably remind you the steps. So the first step would be to solve for x and y and express the function f in terms of u and v, right? So let me just write it down here. The steps. So step one. So we have to solve for u and v and express f as a function of u and v. Step two, you have to compute the Jacobian. Step three is to find the bounds for the region R in the UV coordinates. So find the bounds of R. And then last step, then you can evaluate your integral. By the way, Vzivolod, I hope you feel better now, right?
Yeah, thank you.
Mhm. Oh, sorry. I said solve for u and v. You have to solve. You know the expression of u and v, right? You have to solve for x and y. Sorry, here I said x and y, of course. So we have to express x and y in terms of u and v. Again, the function f in this example is this function inside the integral. It's this xy, right? This is my function f of xy. So once you solve for x and y, so once you express x and y in terms of u and v, then you can express this function f in terms of u and v, right? Well, actually, I don't know the answer of this problem. I mean, final answer. I didn't solve this problem, so I mean, I don't know the final answer. Um, let's see. Yeah, I mean, it could be any number actually. Mm, yeah. Okay. Well, I mean, anyway, that's not a big deal. I mean, we have like 20 minutes. I mean, I have a lot to say about the triple integrals, change of variables and triple integrals. We have many, like a very special change of variables in the dimension 3. So we see like there's this cylindrical coordinates. There's this spherical coordinates in the dimension 3. So we have a lot to say in dimension 3, and of course I'm sure I cannot I mean, I cannot do it like, I guess, today. So what I'm gonna do, guys, after this exercise, I'm gonna give you another exercise about the polar coordinates, right? So these polar coordinates are kind of important. So you need to know kind of by heart these polar coordinates because, as I said, sometimes they are very, very useful. You know, whenever you have like a square root, you know, you have a circle or a disk, then the easiest way to evaluate your integral is to use the polar coordinates, right? So yeah, probably we're gonna do one more exercise, one more example exercise about the double integral, and Thursday I will finish the triple integrals. So then the homework number 3 would be about this this change of variables, right? Did anyone got the Jacobian? I think the Jacobian.
I've just got the answer.
The answer?
Yeah,
what's
I have 7.
7?
Yeah.
All right, let me see. 7. That's weird.
I'm not sure about the bounds of the integral.
I got 1 for the Jacobian.
Yeah, I don't think 7 is correct. I think Anicia is correct.
No, I mean for Jacobian, I have 1 also.
Oh, you have one. Okay.
Yeah, I mean 7 is the final answer.
Oh, final says 7. Final. Oh, you're done. Okay, that's good. Nice. Anicia, did you finish the integral? Did you get the bounds for R of R?
No, I'm doing that.
Okay, I'm gonna give you probably a couple of minutes. All right.
Yeah, bounds. That's what confuses me. I'm not sure because like there's no functions in the bounds. There's only numbers.
Yeah, that's normal. That's okay. So I guess you're gonna get like a rectangle or or a square. That's pretty normal. This is actually a good example. So you know the region D is a parallelogram, right? So the sides, they are not. They are neither horizontal or vertical, right? But then
and it goes to rectangle.
Yeah. But then when you use the U and V, the parallelogram becomes like a rectangle. So then the sides, they are they're horizontal and the vertical with vertical and horizontal sides. Anyway, yeah. All right, so then okay, I can probably write down the second exercise. So because I think some of you are still working on the first one. So if you're done, here's another exercise, and I'm gonna try to do both to solve both of them today, but probably I won't have time. But let me just write down. This is exercise number 2, and so this exercise number 2 is actually about the polar coordinates. So let's say D is the region, so the set of points x, y. So y is between 0 and positive square root of 4 minus x squared, and x is between 0 and 2. Okay. So this region D is just the corner of a disk. So this is just like the first quadrant. So this is 2 here, 2. This is x. This is y. So your region D in this case would be the first quadrant here. Okay, so this is your region D. Okay. So this is, of course, this is a circle. So the boundary here is the circle x squared plus y squared equals to 4. So radius 2. Anyway, so that's our region D. And what you have to do, guys, is to evaluate the double integral over D of the function square root of 1 plus x squared plus y squared dx or dy dx. So if you're done with the first exercise, please try to solve this one here. So yeah, so the point of this exercise, of course, I mean, this integral here, this double integral is very horrible, actually very hard. I mean, it's very complicated to compute, but the idea here, of course, is use polar coordinates. So if you have an exercise, guys, in the homework or in the test, where you have like some double integral with some difficult, let's say, an integral with like a square root, okay? So if you see a double integral with some square root, then you should think of the polar coordinates to evaluate your integral, because they are very, very convenient, right? Whenever you have like a square root, like square root of 1 minus x squared or square root of 1 plus x squared or whatever, you have a square root, think of using the polar coordinates, right? And for the double integrals, of course. Okay, so just let me write it down here as a remark. So whenever you see square root in a double integral, think of using polar coordinates. Okay. Did you get the bounds, Anicia, for R? Do you need more time, I guess? I don't know about David and Enrique. Okay, because we have 10 minutes, guys. I mean, probably that won't be enough for the first one, but yeah. Let's see. Oh, okay. Okay, I'm gonna just give you one more minute, guys, and then I'm gonna try to solve number one. For number two, I probably won't have time. I will do it next time, or I'm gonna leave it as an exercise in the homework. All right. Okay, guys. I'm gonna try to solve number one. I'm not sure if you're done with number one, but I'm gonna solve it anyway because we don't have time, and I'm gonna leave number two as an exercise in the homework, I guess, because the next time I need to start chapter 7, right? Okay, so for number one, yes.
A quick question. Yeah. So when we turn in polar coordinates, the Jacobian will always be R, right?
Yes.
Okay.
Jacobian, yes.
So we don't even need to compute it every time.
Yeah. Okay. Absolutely. Yeah. Very good. Very good point. Yes. Yeah, you don't have to compute the Jacobian again, right? Yeah, it's always R for the polar coordinates. Yes. So I was saying, so for this exercise number one. So it's number one. So for step one, I won't give you all the details, guys, here because that will be too much. But so u is equal to so first step we said it's we have to solve for x and y. Solve for x and y and express f as a function of u and v. All right, so well, u is equal to y minus x, right? And v is equal to minus 2x plus y. So if you want to get x, all you have to do actually is to subtract the first equation from the second one, right? U minus v, so 1, this is 2. So if you do like 1 minus 2, then you'll have actually x, u minus v equals to x, right? And if you do, I think, minus, let's see here. So 2 times, if you do 2 times the first equation, 2 times, oops. So 2 times the first equation minus minus the second one, right? Then you would have y, or 2u minus v, sorry, 2u minus v is equal to y, all right? So we solve for x and y. So then my function, so the conclusion here from the first step, so that's my e, here's my x, this is my x here, here's my y, and so my function f in terms of u and v, so it's x times y, so that'll be equal to u minus v times 2u minus v, okay? Second step, so step 1, step 2, we have to conclude the Jacobian, right? So step 2, oops, so step 2, so the Jacobian, let me just write down the formula again. So partial x, y, with respect to u and v, partial x, partial u, partial y, partial v, minus, sorry, partial x, partial v, partial y, partial u. So partial x, partial u, that's 1, partial y, partial v, that's -1, minus partial x, partial v, that's -1. Partial y, partial u, that's 2. So that'll be -1 plus 2. And so the answer is +1. So your Jacobian is +1. Okay, so again, this is a constant in this example, but in general, Jacobian is not necessarily constant, right? So that's step 2. I'm not doing all the details here, guys, but again, I mean, you can just try to follow the details in the step number 2, right? So how we compute the partial derivatives, etc., etc. So in step 3, we have to find the R. We have to find the R, right? So all you have to do, guys, is write down the equations, right? Like first equation is, so like you have y is equal to 2x, right? So in other words, y, of course you can sketch your region D, okay, but you don't have to sketch the D, okay? But all you need is really just the equations. Once you have the equations, then you can do all the computations. Anyway, so to find R, first equation is y is equal to 2x. So y is equal, like we said, y is equal to, 2u minus v. That's equal to 2x. So that's equal to 2 times x. We said it's u minus v. All right. So you see here 2 times u, 2 times u. So they cancel out. So it's minus. So it's just minus v on the left, minus 2v on the right. So then v is just equal to 0. Right. Next, number 2. I don't have time. I have only 3 minutes, but I'm gonna try to do my best here, guys. Next equation, what is it? It's y is equal to x minus 2. Okay, so it's almost the same thing. It's just so we have minus, so it's 2u minus v is equal to 2u minus v, and then there is a minus 2. So we're gonna have like minus v is equal to negative 2 v minus 2, and so we're gonna have v is equal to negative 2. Right? If you move minus 2v to the left side, that'll be plus 2v. That'll be plus 2v minus v. That'll be plus v. So it's equal to negative 2. So that's another. So we have v equals to 0, v equals to negative 2. Third equation is what is it? It's y is equal to x. It's not that bad. So y is equal to x. Y is equal to x. So then y, we said it's equal to 2u minus v. That's y is equal to x. X is u minus v both sides. So it cancels out. 2u is equal to u. So u is 0. So that's my u is equal to 0. That's my third equation. And the last, number 4. Oops, wrong color. So number 4. So it's y is equal to x plus 1. So y is 2u minus v, u minus v, and there's this plus 1, minus v, cancel out, of course, both sides here. 2u, u on the right side, then we will end up with just plus u on the left. So this is u equals to positive 1. Right, so if you want to sketch the region R, so if you want to sketch R, so R, so this is, so we are in the u and v coordinates. So we need v equals to 0, u equals to 0, we need v equals to negative 2. So this is negative 1, this is negative 2, and we're gonna need u equals to 1. Right, so we have v equals to 0. So here is v equals to 0. This v equals to 0. We have v equals to negative 2. So this is v equals to negative 2. We have u equals to 0. So this is u equals to 0. And then we have u equals to 1. So here's u equals to 1. So my region is just this, this rectangle. My R is this rectangle here. Right? So you can see u is between 0 and 1. And v is between negative 2 and 0, right? So we have this rectangle. That's perfect. That's very, very, very convenient. So u is between, you see, the u is between 0 and 1. And v is between, actually, see, negative 2 and 0. Right? We have this rectangle. That's perfect. And so now we can evaluate, in the last step, we can evaluate the integral. Step 4, probably I won't have time to evaluate the integral, but let me just write down the formula. So over d f of xy dx dy. Sorry, here v is between negative 2 and 0. Sorry guys, I'm just so 1 minute. I'm gonna just need 1 minute, 1 more minute, and then I'm done. So f of xy. F of xy, it's just a sorry, Zivolat, I just need u minus v to u minus v. So this is u minus v here, 2u minus v, Jacobian times absolute value of the Jacobian. Jacobian, we said, is positive 1. So it's times 1 here, time du dv. U is between 0 and 1, and v is between negative 2 and 0. All right, and then this integral is not really hard to compute. Right, so this is easy to compute. Zivolad, you said, let me just see what you.
Yeah, I have the same, and this integral gives 7. Yeah.
Oh, okay. Okay, so you got 7. All right. Okay, so let me, so yeah, okay, perfect. So you're saying this answer here should be 7. Okay, thank you. All right, guys, I'm gonna stop here. I'm sorry, went over time again. So next time I will do the change of variables for triple integrals, right? And then we'll start chapter 7. All right, guys, thank you, and I will see you hopefully on Thursday. Okay, take care, everyone.
Okay, thank you. Goodbye.
Goodbye. See you next time. Thank you. Thank you, everyone.
Thank you, Professor.